Hi, I'm Yiping from Unity Helsinki. I'll be presenting our work on the effectiveness of self-supervised pretraining for modeling user behavior sequences. This is the agenda for this presentation. I will quickly introduce the Unity game advertising solution, and then I will put the focus on the sequential learning and introduce the self-supervised pretraining scheme. Next, I will show how is pretraining network integrated in the downstream task, which is a conversion prediction. Finally, I will discuss the experiment and conclusion. Most people know about Unity by knowing it's the game development engine, but Unity also provides the game monetization solution. One of our products is to select the most valuable ads to show to the users and to optimize the ads conversion rate and revenue. So optimizing the conversion prediction accuracy is an important machine learning problem for us. Here on the right side, it shows in the Unity advertising system, the information we can collect, for example, the target ads and other context information like game, device, and geolocation, user profile, and so on. And lots of information can be used as features to train the conversion prediction model. Besides of the features about target ads and context, we also want to consider about users' historical behavior. If seeing this story example here, there is a pattern about how users interacting with ads. For example, the user tend to click ads when it's weekday evening because maybe in the commuting time in the morning, it is inconvenient to interact with ads. And the user tend to be more interested in puzzle games instead of action games. With the information, we may be able to do better on inferring users' preference. One approach to enhance the prediction power of the conversion prediction model is to learn a representation on user behavioral sequence and use the representation as features to train the conversion prediction model. Based on users' history, we know better about users' preference, so we can show more personalized ad to the user. To process the sequential data, it is natural to consider using recurrent neural network. So users' action, the ads that have been shown, and the time gap information can be used as features in each RNN step. The representation learned from the RNN network can be integrated with the conversion prediction network, or we can train both RNN and conversion network at the same time. However, in practice, we encounter some challenges when learning representation for user behavior sequence. If we learn representation on installs, we have the problem that the installs are sparse, so it's difficult to learn well. Besides, we couldn't fully utilize the information from the sequence itself. Other actions that the user perform, like a view and click, may also indicate the user's interest on certain type of ads. Another way is to learn on the next item, but it is still difficult because the number of next items are large. It is hard for the model to predict the exact next item. Besides, the user's history data is normally noisy because it may be affected by other strategies of showing ads. To tackle those challenges and follow the inspiration from self-supervised learning, we consider to pre-train the representation from data itself without utilizing label information. User behavior sequence may not contain as rich information as images, but still reveal lots of information about users' interests. Getting label is not a difficult problem in conversion prediction task, but we have to wait for the conversion window and also maintain a large database to store and update the outcomes and sequence in practice. If we consider to train both sequential network and dense network in the same time, the sequential network would normally be the bottleneck because it takes longer time to converge. By doing the pre-training, the whole model doesn't have to train from scratch. To continue from the previous story example, predicting the correct target item from other thousands of items is difficult, but we can predict the relative probability of the correct next item among all the negative examples. The process is guided by optimizing the contrastive loss. Here in this story example, the model learns the puzzle game would have higher probability being the next item comparing to the other options. One way to generate negative examples is to randomly draw samples from other sequences. So in the end, the model can learn general representation about the user's preference and how active is the user interacting with ads and so on. More formally, we show all the components of the proposed scheme here. The conversion prediction network has the sequential and dense subnetwork to deal with sequential, categorical, and numerical features. The learning target is to predict if the ad is converted or not. So the learning can be guided by binary cross entropy. The lower part is the self-supervised training network. It pretrains the user's sequence by using contrastive loss, which can be the cross entropy given positive and negative samples. Next, we will show the experimental environment and results. We collect the data from our online advertising system and use 1 month of users' history. In the network structure, we use dense network and glue for sequential training. We use log loss and AUC to evaluate the performance of models. In the experiment, we are interested in the representation learned by the self-supervised pretraining. We visualize those representations by Disney. On the left side, here different colors represent different target items. From the visualization, we can see the representation can have some kind of clustering effect on the target items. Even target items are never used as labels in the pre-training phase. On the right side, we compare the result of linear evaluation and the models training with all labels. In linear evaluation, we freeze the sequential part and use the representation learned in the pre-training phase directly without fine-tuning, and we train the dense network to do the conversion prediction. We also test the scenario that we allow the network to fine-tune using all labels. The model with pre-training still outperform the models without pre-training. Next, we show the training curve and the performance when training the model with different proportions of label data. No matter in the case of limited accessibility of label data or when using all labels, the model with pre-training can achieve comparable log loss and AUC score when training with less label data. Another observation is that when training with very limited label data, 5% or 10%, the information gained from pre-training phase is larger. Those results indicate the proposed pre-training scheme considerably enhanced the data efficiency. To conclude, this work introduced a self-supervised pre-training scheme for modeling users' behavior sequence in conversion prediction task. From the experiment, we can see the models trained with the proposed scheme can achieve better performance in terms of log loss and AUC score and are more label efficient. The next step of this work can be to research different kind of pretest tests or do multi-task training in the pre-training phase. Thanks for listening, and I look forward to more discussions during the Q&A session.